Vasconcelos from Torrey Pines High School, and this is my work on person following UAVs. Imagine a world in which you could have a drone that acts as your personal cameraman, taking videos of you as you shred the slopes of Whiteface. In this work, we will propose an architecture that accomplishes these goals. In this problem, there are two key challenges: achieving real-time speeds and having control over drone behavior. We address these issues with one key idea: having the user wear a pattern badge with 25 different squares that contains two different types of patterns. The first is a control bit pattern, which allows us to locate the badge in the image. And so we can find the badge just by looking for the 2 diagonals or 9 control bits. This leaves 16 other bits available for programming, which is why we refer to them as program bits. And this will be illustrated later in the talk. So here's how we got it all working. First, the drone lifts off the ground and captures video footage of the surrounding. It then takes the current frame and sends that through a badge detection algorithm, which locates the position of the badge in the frame and calculates the error, or the distance between the badge and the center of the frame. This error is then fed into a PID control loop, which calculates the commands necessary to move the drone such as to get the badge back in the center of the frame. In order to make the algorithm fast enough to achieve real-time speeds, we based it off of two key attention mechanisms of human vision: bottom-up saliency and top-down saliency. Bottom-up saliency was implemented using the Harris corner detector, which finds the corners in the image and exploits the fact that the badge has a high corner density. And so this eliminated many of the images or regions in the image, but various regions that contain random objects with large numbers of corners were also sent through. So the output of this was fed into the top-down saliency mechanism, which is a classifier with the goal of figuring out which region actually contains the badge. And we were able to make this efficient by exploiting the fact that the badge is a Haar wavelet and that summations can be made by using integral images. So originally we used the dot product as a similarity measure. However, this produced disappointing results because it was too vulnerable to inconsistent lighting. So we developed a novel similarity measure that sort of averages out the lighting in the image and makes the algorithm much more robust to variations in lighting. So in order to test detection accuracy, we created an image dataset consisting of 312 very challenging images, and were able to achieve a detection rate of 93%. In the beginning, we started only with the top-down detector, and this only achieved a tracking rate of 68%. However, when adding 2 backtracking procedures, we were able to meet the 93% detection rate. You can see the value of the novel similarity measure when compared to the dot product similarity measure because of the 30% increase in efficiency. In order to test tracking accuracy, we created 2 video datasets. In one, we only changed lighting, and in the second, we changed distance between the drone and the badge. And so we were able to achieve a tracking rate of 40 frames per second. Here you can see a video of the drone following me around. Note how it's able to detect the badge despite background clutter and variations in lighting. And here the drone is detecting me at night with the badge illuminated on an iPad, showing how the drone can follow people in the dark as well. And here I'm illustrating the concept of behavior programming by showing the drone 2 different patterns that tell the drone to follow me from different distances. So this one tells the drone to follow me from up close, this one tells it to follow me from far away, and in switching between the 2 different patterns, the drone moves back and forth to follow the different commands.